Okay, this is an introduction to the last thing that we're going to do in chapter 11 of chemistry, and it has to do with molecular geometry. Molecular geometry, this is actually 11.8, but I'm really introducing 11.8 through 11.10, but we'll leave it at that. 11.8 is entitled Molecular Structure. And what we're going to be doing is learning about molecular structure, or it's sometimes called molecular geometry. And just as in the case of actual geometry, molecular geometry refers to the shape of something, what it's actually going to look like. I'm not going to spend a lot of time with this. You can read about it. There's a little section in your book that talks about it. But there are many molecules where the shape of the molecule determines its properties. For instance, water has a shape that looks like this, and that shape is what actually causes it to have some of its properties, including the type of crystal and the way it forms ice, and all sorts of things will take place because of that. If water had a shape like this, water would not act the way that we expect it to. Now that's hard to understand at this point. Let me give one example. That's very common. If you've taken, and I'm sure you have seen a picture of the COVID-19 virus, it has a very particular shape. That's because that's the way that it attaches in, or actually mimics, allows it to infiltrate our body. I'm not doing a good job explaining that, but a good example of a molecular geometry that would matter would be molecules that have an odor to us. They all come in the shape of a ring with attachments on those rings, and our nose is designed to pick up that smell based upon the shape of the molecule. So the shapes of the molecules actually become very, very important as we move along. So what I want to do in this introductory video is just give you some basic terminology. We are going to end up talking about something called electron pairs. We're going to be doing the simplest type of atom, and what we're going to be doing is asking, what does it look like around the central atom? And what we're interested in is the electron pairs, usually around the central atom. So this actually can be somewhat confusing, but electron pairs consist of the bonds, the bonds and the lone pairs, or the unshared pairs of electrons. So you might say, okay, well that makes sense, but actually I don't really like electron pairs. I like the phrase electron regions. So for instance, let's say that we had something like this, which is methane gas. We would say that there are 4 bonds, no unshared pairs. So this would have 4 electron pairs. That's where your book is going to talk about it. Let's say that we had NH3, which is ammonium. And I'm doing this very quick because we don't have a lot of time. But if you did the valence shell, the dot structure, the Lewis structure is what I'm trying to say, this is what we'd have. In this case, I have 3 bonds, and those are actually 3 single bonds, and 1 unshared pair, or 1 lone pair. But what we would say is this has 4 electron pairs. I've noticed on some of your homework that you've turned in, some of you leave this off. But it would actually be better probably to write it like that. And there's 1, 2, 3, 4 unshared pair, or 4 electron regions. Let's say we have water, which is this. Once again, this one has 2 single bonds, but it has 2 lone pairs. And this also, we would say, has 4 electron pairs. Okay, 4 electron pairs. You say, okay, that seems pretty straightforward, and it is, but now let me show you some that are a little bit more interesting, let's say. Let's say we had carbon dioxide. If you do carbon dioxide, this is what you'll get. Now, typically a student will say, well, there's 1, 2, 3, 4 pairs of electrons. But actually, this double pair, this double bond, is going to be treated as a single pair of electrons. And that's why I prefer to call this a single electron region. Right? So in other words, there's one electron region, another electron region. It doesn't seem important right now, but in a minute it's going to, or in our next video, it's going to make a big difference. Here's another one. If I had sulfur trioxide, SO3, do that over here, SO3. That gives you sulfur with a single bond, a double bond, and a single bond. If I ask, by the way, this one would have 2 electron pairs, or 2 electron regions. This has 1 double bond, 2 single bonds. This would be 3 electron regions. Or actually, we would say 3 electron pairs. If this had been SO2, we would end up with that. And if you're counting, we have 2 bonds and 1 electron, 1 unshared pair. This would also be 3 electron regions, or 3 pairs. Okay? So, some of you are confused. So here's what you do. When we take our central atom, whatever that central atom is, we are going to ask this question: how many bonds? And it doesn't matter if it's single, double, or triple. And how many unshared pairs? And that right there will give to you what the electron arrangements around the central atom would be. So I want to show this to you because you actually need to see it. And if you have marshmallows at home, you could play with this. But there's going to be 3 different, I've lost some, yeah, there we go. So let me show you the 3 different basic geometries. There's 3 basic geometries. And your book actually will call this 3 basic electron arrangements. The first one is when you have two electron pairs or 2 electron regions. And that is called a linear molecule. Now, if you think about that word, linear means exactly that. So let me show you carbon dioxide. Carbon dioxide is a linear molecule. It's got 2 double bonds, no unshared pairs. Count those and it gives you 2. And if this is my carbon and these are my oxygens, I'm going to put 2 bonds there and 2 bonds on another one. And what will happen, and I'll explain why in the next video, these will move as far away from each other as they can. It's actually, what's going to happen is these negative regions are going to move away from each other. And that molecule becomes known as a linear molecule. It falls in a straight line. It's a flat molecule. All right? Now, the second possibility is that we have 3 electron pairs or again, I would prefer regions, but I know what your book says. It says electron pairs. And this one we call trigonal planar. Trigonal planar. Now I want to explain that word for you. Trigonal trigonal trigon means triangle. So if you'd rather think of this as triangle, and the word planar, whenever you see that, means flat. It's like a plane, not an airplane that goes in the sky, but a plane like this piece of paper is a plane. And that becomes the second type of molecule. So if I had SO3, that would look like this. And what will happen is I will have 3 carbons, or 3 oxygens in this case. Now, my central atom is a sulfur. This is sulfur. And what's going to happen, we're going to find out, is these are going to move as far away from each other as possible. And you're going to get a shape that looks something like this. And we're going to talk later about the bond angle. This is 120 degrees, 120, 120. You'll remember it's 360 degrees around the triangle. This is a flat molecule. If I turn it like that, it looks flat. But as soon as I turn it this way, it has its shape to it. And we call it trigonal because it forms a triangle, obviously. It does something like that. Okay? And then the last one is when we have 4 electron pairs or 4 regions, and that is called tetrahedral. Now, tetra is the word for 4. Hedral means a 4-sided shape. This would be what you guys would know as a pyramid, but a triangular-based pyramid. So if you think of taking a triangle, let me do it this way, but then take this up to the top like that. That's kind of hard to see, but that is a tetrahedral. So here's what a tetrahedral will look like. By the way, here's what almost every student wants to do, and if you were in class, I would actually have these out for you and you could play with. I would tell the students, I want you to take this and put these as far away from each other as possible. And most people do this, and they say, there we go. Those are as far away from each other as possible. That is a flat molecule. It's not a 3-dimensional shape. What happens is, and again, you could play with marshmallows, a big marshmallow and tiny marshmallows. I actually use spice candies in class, but if I move this to right about here, move this one to here, it's hard to do this well, and then put that one there. That shape has the greatest distance between them. If I've done this right, this angle from here to here is 109.5 degrees, not 90 degrees. This angle is 109.5. This angle is 109.5. And if I've done it right, this angle from here to here is 109.5, 109.5, and 109.5. You would call this a tripod. But it's not a tripod where the legs go out at, say, 60 degrees. This angle between any one of these is 109.5. By the way, I forgot to mention that. That angle is called the bond angle. So on this one, the bond angle is 180 degrees. On this one, if we actually draw it out, our bond angle is 120 degrees. It's 120 degrees around. But when we do the tetrahedral, and by the way, tetrahedral would be something like methane, CH4. If I try and draw that out, it's going to look like this. And one of these would kind of be behind. So you could do kind of a dotted back to here. And it's hard to draw that so it's easy to see, but that's what's taking place. It's better to look at it like this. That is our tetrahedral molecule. So what you need to do for me is read section 11.8. And then there will be an assignment, sorry, I'm kind of close to the camera there, that we're going to try. And that would be problems 69 through 72. So 11.8, 69 through 72 all. And I'm sure there's going to be questions about those, but the number 69 you can pull out of the book. Number 71 as well. And read that section. Read 11.8. And tomorrow or next lesson, we'll talk about 11.9, where we actually start looking at the actual geometries themselves. So that is an introduction. A lot of this will get cleaned up as we go through, but that gets you started into this.